In the vast landscape of physics, one transition stands out as truly transformative: the leap from classical field theory to the mesmerizing realm of quantum field theory. But what does this transition mean? At its heart, classical field theory is a world of determinism and continuity. It is where waves and fields follow well-defined mathematical paths, like the graceful ripples on a tranquil pond. In quantum field theory, the equations evolve, transcending classical continuity. The probabilistic nature of particles emerges, and quantization replaces classical determinism. How do the equations evolve, and what are the new concepts that come into play? In this video, we are going to explore this journey from classical field theory to the mesmerizing world of quantum field theory, where new equations evolve and new concepts emerge. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to Demystifying Quantum Field Theory series, chapter number 4, where we are learning more into classical to quantum, including Lagrangian, Hamiltonian and various other things. Before I go ahead and start with this particular video, I would like to tell you that I've already started few lectures which are live on my channel Physics for Students. I've already done part 1, part 2, part 3, part 4. Now these lectures are not the same as videos but much more mathematical, with certain derivations regarding spontaneous emissions, Schrodinger's equation, standard model, etc. These videos are live, so I come online around about 8:30, 9 p.m. Indian Standard Time, and you can very well participate. Ask me question because I will be live. I've already done 4 lecture videos live on quantum field theory, and the 5th is just waiting. I'm hoping to make it maybe tomorrow or in the coming future very quickly. So these are the lectures which you can participate. Let us now go into the main video, where we would be first starting into the transition phase, which is called understanding a little bit more into what is a classical and a quantum plane waves. Now you see, a classical wave is basically a kind of a disturbance in a physical medium that can propagate through space and time. Here you can see that I have written that it has a constant amplitude and frequency and a constant direction of propagation. So classical waves can be transverse, where the oscillation is perpendicular to the direction of propagation, or longitudinal, where the oscillation is parallel to the direction of propagation, and it can be divided into water waves, sound waves, light waves and so on. This is quite known to us. Now, in case of a quantum plane wave, it is a special type of a quantum wave function that describes a particle that has an infinite wavelength and a definite momentum. So quantum plane waves, they look like this, as I have shown you on the right hand side of the screen, are often used in quantum mechanics to model the behavior of free particles, such as electron in a vacuum. So this is basically a basic definition in what is a classical wave or a quantum wave, but there are more things just to discover and make things very precise. Now here is the definition of this is a kind of a pressure plane waves which is moving in a three-dimensional physical space, and this is again a wave function which is moving in three-dimensional. Here you see that the plane wave I mentioned is P1, P2 and so on, and this is mentioned with the wave function which is psi1, psi2 and so on. So here you can see that I have shown that this part is actually the real part and carries the wave, the normal classical wave equation, and this is given by the wave function. So what happens here is that the numerical values of the waves on each plane, I mean to say versus the spatial position, is given at an instant time. So the complex waves, as you can see, has 2 components to plot. The real wave, only one. So plane wave packets for both pressure and wave functions can be built up with the superposition of many pure sinusoidal waves. So here P is real, RE, e to the power ikx, which is a classical wave function, and here it is psi equals to ae raised to the power ix, which is the quantum wave function. Now another very important difference is this one, that quantum wave function is not observable by itself. That means it only allows you to compute the probability distributions of observables. So if I take a kind of a, I would say, you need to describe 2 particles with the help of a wave function. Classically, you may say, you may expect one of the 2 possibilities. That is, if I'm mentioning is as psi, it can be on one hand can be psi x, which is you may think that they correspond to some wave packets in a single classical field, that is psi x. On the other hand, you may think that they are described by two classical separate fields, that is psi x1 and psi 1 x1 and psi 2 x2. And these are actually two separate classical fields. So the quantum reality here is something different. So in quantum mechanics, what happens is that you have to describe them by a single wave function, as I was telling you, it is a superposition depending on both coordinate, not factorizable into two separate pieces. So you see psi x1 comma x2 is not equal to psi 1 x1 and psi 2 x2, which happens typically in case of a classical wave. So here is it. In quantum mechanics, a particle which is described by a wave function psi, which generally is a complex valued function. The wave function need not to be a wave, but it can be a wave. So first is that, as you can see, the basic difference, this is something technical, two wave packets of the single classical field psi x. So what I have tried to do is that to describe the particles with the help of wave functions, you might expect two possibilities. One, a single classical field. On the other hand, you might think that they are described by two separate classical fields, psi 1 x1 and psi 2 x2. And the quantum reality is that the single wave function depending on both coordinate generally is not factorizable. So this is a kind of a mathematical description of what is the difference between a classical and a quantum plane waves. However, there are a few more points which is good to learn before we move ahead into quantum field theory. The first is that it is described by classical physics. The second is that waves are often described by what is called classical wave equations. Also, classical waves are typically characterized, as I have shown, by amplitude, frequency and wavelength, and waves can carry energy and information and can be described by using simple mathematical, continuous mathematical functions. Quantum waves, on the other hand, are a fundamental concept of quantum mechanics. Plane waves are generally described by Schrödinger equation, which is a fundamental equation of quantum mechanics. Unlike classical waves, quantum plane waves are probabilistic in nature. That means they do not carry enough amount of energy or information directly. And quantum plane waves are characterized obviously by a wave function, which is a complex value function, which is not a real function. Moving ahead from here, what we find, if I turn the pages, we find that it is determinism and probabilistic. That means classical waves are determined, that can be precisely described by using continuous mathematical functions, while quantum waves are probabilistic in nature. Classical waves can carry energy and information by their when they propagate through space, whereas quantum waves have probability distribution. Quantum plane waves are a manifestation. The classical waves are typically described using classical wave equation, whereas quantum waves were described by using Schrödinger's equation. Also, quantum plane waves are a mathematical, I would say, manifestation of the wave-particle duality, which implies that particles can exhibit both wave-like behavior at the quantum level, and classical waves are definitely not, I would say, exhibit particle behavior. So here is a kind of a quick summary, and the summary: classical waves are continuous, deterministic of macroscopic level, while quantum plane waves are probabilistic, representing the quantum behavior of particles with wave-particle duality. So the key difference lies in the probabilistic nature and the dual behavior of the quantum plane waves. So having understood classical and quantum, because we will be dealing with this particular wave more and more as we move into quantum field theory, what is important now is to understand that when we move from classical to quantum field theory, there are certain equations, there are certain concepts that changes. What are those concepts, how it changes, and how it makes a difference taking from classical to quantum? Coming up in the next part of our video, we will be looking more into the classical and quantum field theory, how things change. Now see, classical field theory is basically a branch of physics, as you can see, that describes how physical fields interact with matter. So on the left hand side, what you can see is a schematic diagram that tells that how physical fields interact with matter. So physical field is what is a quantity that is assigned to every point. Here you can see this is a field. So it is a physical field that is assigned to every point, those black arrows pointing in the space and time. So for examples, with physical fields include the electromagnetic wave, the gravitational waves. And here what happens is that the gravitational and the Higgs field is also taken into account. So in classical field theory, typically fields are treated as continuous quantities that can take on value. This means that fields can be infinitely subdivided and there is no limit to the precision with which they can be measured. Also, classical field theory are typically formulated using the Lagrangian formalism, and Lagrangian is a function of the field and its derivative, and it describes the action of the field. In summary, we can say that classical field theory is a branch of physics that describes how physical fields interact with matter. Now, having said and defined all this part, what I would like to tell also is that this part of the Lagrangian formalism, etc., actually also changes, as we will see how the classical Lagrangian will change and what are the things that are happening. But this is taken into account what is a classical field theory. What about the quantum field theory? Now you see, in quantum field theory what happens is that the field starts interacting directly with the particles. Here what has happened is that here fields have the physical field starts interact with matter, but here is that what happens is that physical field starts interacting with the particles. So quantum field is a theory of branch how physical fields interact with particles. A particle is considered to be a localized excitation of the physical field, for example in electromagnetic excitation. This also means that I would say fields are treated as quantized quantities. That means these fields can only take certain discrete values. Now, quantum field theory are typically formulated using the Hamiltonian formulation. The Hamiltonian is a function of the field and its conjugate momenta, and it describes the energy of the field. So this is actually what is the difference between classical field theory and quantum field theory. Now, because we are taking classical field theory right as our root, I need to tell you that what exactly is a formulation of classical field theory and how it moves. So for the time being, what I'm going to consider is that I'm going to consider a kind of a smooth trajectory, that is this one. For example, a position of a particle in one-dimensional straight line or say curved line. So any smooth trajectory q of t of this variable, which will have a time interval between t1 and t2, regardless of whether the trajectory obeys wave functions or of motion, or it is a completely random, I would say, walk, then it would be defined using the action integral, which is this one. It is quite known. So here what happens is that this one is considered to be the Lagrangian in the formula LQ, and you can see a Q dot, which you can understand very well, and this can be written as this one, which is the kinetic energy minus the potential energy. So now in this concept, the integral that you are seeing, the Lagrangian, is an ordinary function L of two variables Q and Q dot. So okay, so this would lead to this, yeah. So this integral is of two variables Q and Q dot, evaluated by Qt and this one. And this is for the specific trajectory qt for each time t. And this also means that on the other hand, the action s is basically a functional of the entire trajectory q of t. That also means that it is the entire history of the motion rather than any value of the particular time. So you see that Lagrangian actually takes the entire history of the motion rather than of a specific time. Now, having said and defined what is Lagrangian in terms of classical field theory, now it is the time we should say what are the changes and how things changes from classical to quantum field theory in terms of equations. Let us look in the next part of our video. So in this part of the video, we are going to look into what is called the changes of quantum field theory, equations of motion, classical Lagrangian and Euler-Lagrange equation. So from classical mechanics, we know that the Lagrangian of a particle, I would say, which is a kinetic energy minus potential energy, is given by this and this. I hope I don't need to explain it further. I'm considering 3 dimensions, so I have taken the variables from 1 to 3. Now we can also find out the three-dimensional motion of the particle, obviously using the Euler-Lagrange equation, which actually shows like this, where this part is actually the Lagrangian, that is the kinetic minus the potential energy. Now what are those terms? I mean to say, it is always a good time to explore and understand the Euler-Lagrange equations. Let me quickly explain you what are those terms, and then we will see how the transition actually takes place. Okay, so here is the equation. So we have already defined L is a function that summarizes the dynamics of the system T minus U. First we will take into this, right? So this one is what is called the partial derivative of L with respect to x dot I, and this is basically what I can tell, the term represents the partial derivative of the Lagrangian with respect to the time derivative of the generalized coordinate, which is xi, which is denoted by this, and it is also known as the generalized momentum, which is obviously associated with the general coordinate x. Now if I take this one, the entire d by dt and the entire, this is called the time derivative of the partial derivative, right? So this term actually represents the time derivative of the generalized momentum with respect to time. In other words, we can say it describes how the momentum associated with the coordinate this, right, xi is changing as a function of time. So it is a time derivative of the partial derivative, and it also tells that how it is changing with the function of time. This particular part, partial derivative of L followed by the denominator partial derivative of xi, is basically the partial derivative of L with respect to I. This term represents the partial derivative of the Lagrangian with respect to the generalized coordinate xi, and it quantifies how the Lagrangian on the coordinate actually changes. So here you see it actually basically shows the partial derivative of L with respect to xi. This term represents the partial derivative of the Lagrangian with respect to the general coordinate xi, and it quantifies how the Lagrangian depends on the change of the coordinate, which is x. Now this 0, as we know that it is actually set equal to 0 because this is a consequence of the principle of least action, which actually states that the actual path taken by a particle minimizes during the action. So this is all in all what we call the Euler-Lagrange equation component by component. Now when we move next from this equation, if we get this and this equation, we already have got into this. So this actually shows that we can reduce the Newton's second law into this one, which is actually equals to this. Now what is actually I would say what is actually left is that for a system of particles, now this second law of motion also uses the conservative force. Now for a system of particles, we need only to add an extra kinetic and potential energy terms, which I have not done to make things easier. And for each additional particle, if we want to make it relativistic, then we just need to add the relativistic kinetic and potential terms instead of the Newtonian terms, and things will become much more clearer. Okay, so from here what we see that if you're given a kind of a Lagrangian, for example L, this is very important. We could also find out the Hamiltonian H via the Legendre transformation, which is something like this, right? So what I'm trying to tell is that if you're given a Lagrangian, we could find out the Hamiltonian H via the Legendre transformation, and which looks like this, where this one is equal to this. I think this is quite clear, right? I am denoting this pi. Now what is important over here is this pi is actually the conjugate, or you can say a canonical momentum of xi. Now here you denote, I've used something which is called a co and a contravariant component or a tensor or vector. So you need to note that the contravariant component in the denominator, right? This one, the contravariant component in the denominator, which comes just as the upstairs indices, right? So the contravariant component in the denominator is effectively equivalent to the covariant component, this one, of the entire and identity. And similarly, the covariant component of the entire and identity is actually forming and effectively equivalent to the contravariant components. So now the question is that we get the equations of motion, we got the Lagrangian, we got the Hamiltonian. Now what is the relation? I mean to say, how does it actually affect? We saw the formal Lagrangian, and from there we moved into this, and we transform Newton's equation of motion if it is given the Lagrangian and the Hamiltonian via the Legendre transformation. So here is the relation. So if I get this equation, we get this equation, and we get this equation also. And if I take the Euler-Lagrange equation, then what we get is that the Lagrangian equation L also tells the equations of motion, right? Because we saw that with Newton's second law, and the equations of motion are also going back to the Lagrangian L. So that is why two arrows. Similarly, the equations of motion are also showing the Hamiltonian H, and this Hamiltonian is also going back to the equations of motion. So here is that by knowing any one of H or L, the equations of motion, we can deduce the other two. This is very important. Why? Because I will now show you that we have established that these equations of motion are interchangeable. Getting L and H, we can deduce the other, and both of them are related to each other. What are the transitions of the equation from the classical to the quantum field theory? Let us look in the next part of the video, where we are going to explore how these equations actually change. Now here is the typical, I would say, the Lagrangian, classical Lagrangian, and we have the Lagrangian density, which is this curly L. Also, what we have that instead of time t as an independent variable, we have this one as independent variable, and this one xi would be the independent variables. Also, what we see, instead of a particle which is defined by this, right, xi of t, we have a field which is described by this, and we can also say it is this, and this R actually designates different types of fields, or possibly we can say different spatial components of the same vector fields, which can be the electromagnetism, which is E or B. Now this is actually very central. So the original classical Lagrangian is getting transferred to the Lagrangian density. Time is also getting into x0, 1, 2, 3, etc. And instead of particle described by this one, we have a field which is this, and this R is actually denoting spatial components of the same vector. So now that we have understood this, so let us see that what are the changes that are happening. So this gets into this, t gets into x mu, this gets into this, and the classical Lagrangian, which is the t minus v, also is the same, but however this is known as the Lagrangian density. From here what we get, the Euler-Lagrange equation also transferred here, and the Legendre transformation for the Hamiltonian, where given as pi r being the conjugate, also gets into this, where obviously pi r will be equal to this. Now these are the transition of equations from classical to quantum field theory. Now everywhere you will see what comes as a prime importance, very much important, is what is called a Lagrangian density in terms instead of the original classical Lagrangian. Now what is Lagrangian density? Why it is considered to be so important? Coming up in the next part of the video. So the Lagrangian density is often denoted as this curly L, is a fundamental concept in the quantum field theory. What it happens is that if I take a field, it defines it as a density function, right? It is a density function defined in terms of fields and their derivatives over space-time. Now Lagrangian density also plays a crucial role in terms of quantum field theory, and it is distinct from Lagrangian used in classical mechanics. Here you see these blue dots, these are basically the particles. So what happens is that in classical mechanics, the Lagrangian is a function of those generalized coordinates. I've used certain qi dot, doesn't matter, earlier I have used x. So these are basically the generalized coordinates, usually represented by this, and it describes the dynamics of system of particles, which are the blue one. Now if you take a kind of a quantum field theory, as you can see here, instead of dealing with individual particles, we are now working with fields such as scalar fields, vector fields, tensor fields, and which are continuously distributed over space-time. So the Lagrangian density is a function that depends on those fields of their space-time derivatives, which is written as this. And here this phi x is actually represent the field, and this one represents space-time derivatives. right? So this is basically the transition from the Lagrangian, why we need as the Lagrangian density as the density function instead of dealing with particles. Now we are dealing with much more wider fields, and the field and the space-time derivatives are mentioned as that. A few more important points before we go more into the Lagrangian density is that the equations of motion, because it is the starting point for deriving equations of motion for the fields which describe how the fields evolve over time and space. These equations are obtained by applying the Euler-Lagrange equation to the Lagrangian density, and ensures that the fields follow the least path action. This is very, very important. So it follows the least path action. That is why it is set to 0, which I have shown you a few seconds earlier. Also, the action path integral formalism, because Lagrangian density is used to define the action, which is a central quantity in quantum field theory. The action represents the total change in the field configuration over a space-time interval, and the path integral formulation of QFT is a powerful tool for calculating probabilities of different events, and is also based on the Lagrangian density. The Lagrangian density encodes the symmetry of the theory, such as Lorentz invariance and gauge invariance. These symmetries are very important to understand conservation of laws, and such as conservation of energy and momentum. What follows further is that Lagrangian density is crucial in terms of quantum field theory, because it provides a unified and elegant framework for describing the behavior of fields and their interaction. It allows us to quantize these fields, which is a fundamental step in developing a quantum description of particles and their interactions. The equations of motions for fields in quantum field theory are derived from the principles of least action. The real numbers and the operators in classical mechanics, these are generalized coordinates and momenta. These are treated as real numbers. Here it becomes quantum operators. So the Lagrangian density provides the foundation for creating quantum field operators. Also, lastly, what I would like to mention is that continuous and discrete classical Lagrangian typically describe the motion of a finite, and it deals with that exists at every point of time. There's a classical limit. The Lagrangian density approaches the classical Lagrangian, and the space-time dependence, the Lagrangian density is a function of time, the space-time coordinates, reflecting the relativistic nature of quantum field theory. The classical Lagrangian, on the other hand, is typically independent of time. So this completes our today's video, which is extremely important in terms of understanding how things move from classical field theory to quantum field theory, and how the continuous, discrete and the Lagrangian density, why it is considered to be very, very important. Time to quickly summarize today's video. We dealt with classical and quantum wave. We saw the differences. Classical and quantum field theory, how Lagrangian and Lagrangian density got generalized, and how we can obtain the equations of motion if we get one Lagrangian and Hamiltonian. We also saw the Euler-Lagrangian equation, how it looks like in quantum field theory, and we also saw that classical Lagrangian and Hamiltonian to Lagrangian Lagrangian density and Hamiltonian density. We understood and evaluated the importance and the basic points which are very important to understand the Lagrangian density. Thank you very much for those who are watching this video. I would request you, if you have liked the video, please hit on the subscribe button to get more notification from Physics for Students. This is my email ID, and this is my other channel on general theory of relativity. You can further follow me on my Facebook, Instagram, LinkedIn and Twitter account. So I would continue with further lectures on quantum field theory, as well as I am coming live to describe more on the mathematics and explain them. So you can watch it, and Physics for Students will be soon back with more interesting and surprising videos. Till then, goodbye.